Hello friends, today we will discuss stresses in a concrete pavement by Westergaard method. And stresses in a concrete pavement occur because of two reasons. One is the wheel load, another is the temperature variation. So stresses are because of wheel load and because of temperature. The stresses because of temperature can further be classified as warping stresses and friction stresses. Because when there is a temperature variation between top and bottom of the concrete slab, then the slab will warp. That is called warping stresses. Now this warping movement is registered by the friction between the slab and the base foundation, base course. That is the frictional stresses. Today in this session, we will discuss stresses in a concrete pavement occurring because of wheel load. These temperature stresses and frictional stresses we will discuss in the next session. Westergaard method of analyzing a concrete pavement was introduced in 1920 to 1930s, but this still forms the basis of many modern design methods. Three different loading conditions are considered in the Westergaard method of analyzing a pavement, and these are: if this is the concrete slab, these positions are internal position, edge loading and corner loading. Internal position is when the load is applied inside the slab, not necessarily at the center of the slab, but when there is no effect of edge or corner, that is the interior loading. This is the edge loading, can be here, it can be here or here or here. And corner loading is when the wheel load comes at a corner of the slab. Now, it is assumed in the Westergaard analysis that the slab is a thin elastic plate and it rests on subgrade, which is liquid subgrade. And this subgrade will provide reaction to the load applied on the pavement. And this reaction is in the form of upward force, and this upward force is proportional to the deflection in the slab. This upward force provided by, or upward reaction provided by the subgrade is proportional to the deflection in the concrete slab, and therefore this P is K into delta, where this K is the constant of proportionality, and this is called modulus of subgrade reaction. K here is modulus of subgrade reaction, and it can be found using plate load test. And I have a separate video on determination of modulus of subgrade reaction. You can watch for the procedure of finding K value, but this is the pressure sustained by the subgrade at a deflection of 0.125 centimeter. So its unit is pressure by meter, that is kg per meter cube, or you can say megapascal per meter. Now, two parameters are defined by Westergaard. One is radius of relative stiffness, that is small l. It indicates the resistance offered by the slab and the subgrade to the deflection in the pavement. And this radius is given by this equation. L is equal to EH cube upon 12 into 1 minus me square into K power 0.25. E is the modulus of elasticity of the concrete, H is the slab thickness, mu Poisson ratio of the concrete, K the modulus of subgrade reaction, K. And L is the radius of relative stiffness, and its unit is centimeter or meter, as you take the unit of E, H and K. This was derived by Westergaard himself. Another important parameter in this is the radius of resisting section. Resisting section. When a load is applied here, there is a small area of the pavement slab which will resist the bending moment in the slab, and this radius is denoted by B. Now this B is either equal to A or slightly less than A. A is the radius of loaded area, and that depends upon the thickness of the slab. If thickness of the slab, let us say, is H, then this B is given by 1.6 A square plus H square minus 0.675 into H. H is the slab thickness. Now this equation is when A is less than or equal to 1.724 H. And if it is more than 1.724 H, then B is equal to A. So B is equal to A. So this is the radius here, which is slightly less than A or equal to A, which will resist the bending moment or resist the moment in the slab. So if, let us say, the thickness of the slab is 20 centimeter, A is the radius of loaded area is 15 centimeter, and therefore A upon H is 0.75, which is less than 1.724, and therefore this equation is to be used. And B, if you put all these values here, 1.6 into 15 square, that is A, plus 20 square, that is H square, minus 0.675 into 20. And this value is 14.07 centimeter, slightly less than the radius of the loaded area. Now with these parameters, three equations were suggested to determine the stress in a concrete pavement. Now, if this is the slab and a load is applied here, let us say, this is the center of the load. If you apply a load here and look at the deflection profile of this slab, this will be like this in the elevation. Now here you get the maximum, at this point you get maximum deflection, maximum curvature, radius of curvature of the slab at this point just below the load, and maximum bending moment will also occur at this point. Maximum bending moment will occur below the load. If you look at the bending moment diagram, it will be something like this, that maximum bending will occur here and like this, and then you have a reverse bending beyond certain distance. That is the compressive bending. At the top there is a compressive stress, at the bottom tensile stress. Now beyond certain distance, what is that distance? Beyond certain distance, that is, if you draw a circle here, this is the L, that is the radius L. L we defined. This is what we call the point of contraflexure. Point of contraflexure occurs at a distance L. L is radius of relative stiffness, and here at this point the bending moment is 0, and beyond that there is a reverse curvature in the slab. The reverse curvature in the slab, and the maximum tensile stress will occur at the top of the slab at a distance of, which is 2.5 times L. 2.5 times L. That is how the stresses occur in a slab when you apply a load in the interior. Maximum bending moment will occur at the center, that is below the load. At a distance equal to L, bending moment will be 0. And at a distance equal to 2.5 L, there will be reverse bending and maximum tensile stress will occur at the top of the slab. When you apply a load at the edge, it will basically, because there is no support here, so it will provide a bending in this direction. So there will be tensile stress at the top, at the bottom, and compressive stress at the top. When you apply a load here at the corner, then the stress will be at the diagonal of the corner of the slab, and this will be tensile stress along this, and maximum tensile stress because of load at the corner will occur at a distance equal to D. I will tell you this T distance. It does not occur at the point where load is applied or below the load, but this tensile stress will occur at a distance equal to D. Okay. So equations given by Westergaard for calculation of interior stress, that is SI, is 0.316 P upon H square into 4 log on base 10 L by B plus 1.069. The edge stresses will be 0.572 upon H square into 4 log L by B plus 0.359. And similarly, corner stress is 3P upon H square into 1 minus A square root upon L to power 0.6. These are the equations suggested by Westergaard. Here, P is the wheel load, H is the slab thickness, L radius of relative stiffness, B is the radius of resisting section, and you can find out what is the stress at the edge or corner or the interior. Let us take one example. Example is that a concrete slab is subjected to corner loading, given that K is 2.7 kg per centimeter cube. The slab thickness is 25 centimeter. A radius of loaded area 15 centimeter. The wheel load is, let us say, 4000 kg or 40 kilonewton. E value of the concrete is 30 GPa, that is gigapascal, or you can say 33 into 10 to the power 5 kg per centimeter square, and mu we can assume 0.15. Let us find out what is the stress at the corner. When this load is applied at the corner, what is the stress? Now that requires calculation of L. So L, let us calculate L first, that is EH cube upon 12 into 1 minus mu square into K power 1 by 4. E 3 into 10 to the power 5, H 25, mu 0.15, K 2.7, and this is equal to 110.3 centimeter. When you put all these values here, this is 110.3 centimeter. Now put this value here, so you get the corner stress 3 into 4000 upon 25 square 1 minus A is 15 centimeter square 2 upon L 110.3 power 0.6. This is equal to 12.05 kg per centimeter square. This is the stress. This is the stress which will be created by this wheel load when it is applied at the corner of the slab of 25 centimeter thickness. Now, as I told you, this does not occur, the maximum stress does not occur at the center of the load, but it occurs at some distance. This is the corner, and if you draw a diagonal here, this will occur at this point. Now, this is D. D is equal to 2.38 square root of A into L. In some books, you will find this factor a different value. But if you look at the original paper of Westergaard, which was published in April 1926, this value is 2.38. So if you put the value of A equal to 15 centimeter, L 110.3 centimeter, this will be like 96.8 centimeter. So maximum stress because of a load here, load of 4000 kg here, maximum stress will occur here, which is equal to 96.8 from the corner on the diagonal. So if the stress is more than the flexural strength of the concrete, the crack will appear along the diagonals in the transverse direction, perpendicular to diagonal. If you want to find out what is the edge stress because of this load or interior stress because of this load, you can put the value of PL. Now you need to calculate B also. B will be square root of 1.6 A square plus H square minus 0.675 H. Because A upon H is 15 by 25, which is less than 1.725, and therefore we should use this equation to calculate. This is x square root of 1.6 into 15 square plus 25 square minus 0.675 into 25. This is 14.5 centimeter. That is the value of B. Put value of P, H, L, B, all are known in this equation, and this will be equal to 9.29 kg per centimeter square. And similarly, for edge loading, put value of P, H, L, B in this equation, and this is 14.22 kg per centimeter square. That is the corner stress, edge stress, interior stress. Now, if you look at these values here, you will find that this SE is the highest of all the three. Corner loading or corner stress is less than edge stress, and edge stress is more than both of these. When experiments were conducted by subsequent researchers after Westergaard, they found that these equations underestimate the corner stress. Corner stress is higher than the edge stress. And this is the critical position. This becomes very critical position when there is no support provided on the corners. And therefore, these equations were slightly modified to give the results which are close to experimental values. The edge load stress equation was modified by Taylor and Sutherland. It is given by this equation. SE is equal to 0.529 P upon H square into 1 plus 0.54 mu into 4 log base 10 L by B plus log B minus 0.4048. And similarly for corner loading, The equation was given by Kelly, and that equation is 3p upon h square into 1 minus a square root of 2 upon L power 1.2. Here in this equation which was suggested by Westergaard, this power was 0.6. It is now 1.2. These are modified equations. And if you again take the same example and find out what is the edge stress and corner stress by these two new equations, you will find that this is now 15.57 kg per centimeter square. Earlier this value was 14.22 kg per centimeter square. So slight increase in the edge stress because of edge loading. But when you substitute value of P, H, A and L in this equation, this stress is now 16.55 kg per centimeter square. Earlier it was 12.05. So this is now more than the edge stress at the edge because of loading. There are certain limitations of this Westergaard theory. The first is that it involves simplification of the problem of wheel loading on a slab by assuming that the contact area is circular. In most cases, the simplification is reasonable even though the contact area is usually closer to a rectangle than a circle. The assumption of a circular contact area leads to only a small error and is very conservative. In fact, in all subsequent analysis, this contact area is taken as a circular area or elliptical area. The second is that slab is large enough so that the interior loading condition is not affected by the slab joints. And research has shown that the Westergaard analysis equations are applicable for slab larger than 3.5 times the radius of relative stiffness. The third is the design of rigid pavements by Westergaard method assumes that there is no structural connection between the slab and any adjacent slab. This is usually very conservative, as there will always be a considerable load transfer between adjacent slabs. In fact, when we use double bars between two slabs, the function of double bar is to transfer the load. And a properly designed and constructed pavement will usually transfer at least 75% of the load across the joint. And the last is that there is no allowance in the design of rigid pavement by Westergaard method for stresses produced by environmental factors. Changes in temperature will warp the slab producing stresses. During the day, the slab will warm, producing tensile stress in the base of the slab, and during the night, the slab will cool, producing tensile stress in the surface. Temperature changes will also cause the slab to expand and contract, producing frictional stresses from the underlying subbase. These are not covered in Westergaard analysis. In the next part of this session, we will consider the temperature stresses and friction stresses and how these stresses, load stress and temperature stresses, make the worst combination for the design. Thank you very much for watching this video. If you have any question, you can write in the comment box.